Hi, today I'll be talking about dimension-free bounds for convex function chasing. This is joint work with CJ Argue and Anupam Gupta, both of whom are at CMU. Let's get started. So you're given a convex function f1 that maps from the d-dimensional Euclidean space to the non-negative reals. So in this particular case, I've denoted f1 by drawing its level sets. X star is the minimizer, and I've drawn the level sets for values 1, 2, and 3. You're also given a point x0, and you want to move to a point x1 to minimize the function evaluation cost, i.e. the hit cost, and the movement cost, which is the norm of x1 minus x0. So maybe the algorithm chooses to move to x1 over here. Notice that the movement cost is 4, and the function evaluation cost is 2. So in total, the algorithm pays a cost of 6 at this time step. Once it moves, the algorithm is given a new function f2, which is also convex and goes from the d-dimensional Euclidean space to the non-negative reals. Once again, we play the same game. So maybe the algorithm chooses to move to x2 over here. Now it pays a function cost of 4, and it pays a movement cost of 6 for a total cost of 10 in this time step. So we keep track of the cost at each time step. So in the first time step, it suffered a cost of 6. And in the second time step, it suffered a cost of 10. So in total, we've paid 16 units. We continue on, and it's given a new function f3. Here I've drawn the level sets again. And it pays a cost of 1 for the function cost and a movement cost of 3 for a total of 4 units in this time step. So in aggregate, the total cost that it paid in step 1, 2, and 3 is 20. So this is the cost of the algorithm. We would like to know what is the benchmark. How do we determine what is a good algorithm? To answer this question, we look at opt. So opt is the algorithm that knows the entire sequence of functions beforehand and can choose a path of points, y1, y2, y3, knowing this full information. Notice that this is quite an unreasonable expectation, as opt in some sense knows the future when it chooses points at y1, y2, and y3. Throughout the rest of the talk, I'll use y to denote the optimal algorithm's choice of points, and I'll use x to be the algorithm that we define the points that it chooses. So if you believe the costs over here, then the cost of opt is in total 17.5. But that's because it moved a total of 11 plus 2 plus 1, and it incurred function costs of 1, 1, and 1.5, respectively. The goal is to minimize the competitive ratio of our algorithm with respect to this optimal algorithm. So in this case, the cost of alg was 20, and the cost of opt is 17.5. Okay, let's define the problem formally. We're given convex functions f1, f2, all the way up to ft. And these go from the d-dimensional Euclidean space to the non-negative reals. And we must output points x1 through xt. And because it's an online algorithm, we must output point xi before receiving fi plus 1. The cost after capital T steps is the movement cost, which is the norm of xi minus 1, and the sum of the hit costs, which is the sum of fi xi. And here, and throughout this talk, norm will denote the L2 norm. And we would like to come up with an algorithm that minimizes the competitive ratio. That is the cost of the algorithm divided by the cost of opt. I want to emphasize that the algorithm does not know capital T beforehand. So in order to maintain a good competitive ratio, it must do this after every request. It must make sure that the cost of the algorithm is at no more than the competitive ratio times the cost of opt. Okay. You might ask why you would study this problem, but this problem is very closely related to a number of problems that arise in the online algorithms literature. In particular, it tackles problems like metrical task system, the K-server problem, which in turn generalizes natural problems like paging. This problem has also been used to model power management in data centers. And it also considers some classical convex problems like convex body chasing. which is just the special case where each fi is the indicator of some convex set. So this problem is quite general and captures a wide variety of problems in the literature. There's a lot of related work in this field, and I don't have time to do it justice. I'll just mention two salient points. The first is that this problem was introduced by Lineal and Friedman in '92, and in their original paper itself, they gave an omega square root d lower bound. So if d is very large, this shows that you cannot hope to do better than square root d. And in last year's SOTA, there was a order d competitive algorithm that was given. So this ratio is almost tight if d is small. However, when d is large, these bounds are quite pessimistic. So let me just summarize. There, in last year's SOTA, it was shown that there exists an order d competitive algorithm for chasing convex functions in d dimensions. However, in many applications, especially in modern machine learning, d is very large. However, the functions themselves have quite a lot of structure. So in this paper, we consider two special cases. The first is well-conditioned convex functions, and the second is convex functions that are supported on affine subspaces. So these are functions who take on value infinity in everywhere except for an affine subspace. So let me, before I state our result, let me define what well-conditioned convex functions are. A function is alpha strongly convex if intuitively it's not too flat. And we say a function is beta smooth if it's not too smooth. So pictorially, what this means is that every function above the bottom black line is alpha strongly convex. And for any function f that lies below the top black line is beta smooth. And we say a function is alpha strongly convex and beta smooth if it lies in between those two curves. Intuitively, what this means is that the function grows at a steady rate that's not too small and not too large. And the condition number is the ratio of the smoothness parameter to the strong convexity parameter. So now I'm ready to state our results. So for well-conditioned functions, we show that there exists a square root kappa competitive algorithm for kappa well-conditioned functions. In particular, note that kappa could be much smaller than the dimension, and hence the title that these are dimension-free bounds, competitive ratios. We also complement these results by showing a lower bound, which shows that there exists a family of instances consisting of kappa well-conditioned convex functions such that any algorithm must suffer at least a competitive ratio of kappa to the 1/3. For the affine subspace chasing problem, we show that there is a min of k and square root k log t competitive algorithm for chasing convex functions which are defined on an affine subspace of dimension d. Although you can find all the results in the paper, in this talk, I'll primarily focus on the first result, which is an upper bound for well-conditioned convex functions, So the first idea you might consider is to draw a line between xt minus 1 and x star, which is the minimizer of the new function ft. And we would like to choose the point xt such that the movement cost is equal to the hit cost. Since we pay both, it makes sense that we should try and equalize these constants. And this idea actually does yield some results. In particular, move to minimizer is a theta k kappa competitive ratio on kappa well-conditioned functions. I emphasize that this is a theta k kappa because we show that this algorithm is actually tight. You cannot hope to improve the analysis. And this is not the promised square root kappa competitive ratio. And by looking at this picture, we can try and understand why. In particular, the algorithm moves a lot in the direction towards x star, even though the function value is decreasing at a very slow rate. So it's natural to try and come up with an algorithm that doesn't do this. And that leads to our next algorithm, which is the online balanced descent algorithm. So the algorithm is as follows. At any given point, we will project xt to be the projection on some level set. And we'll choose the level set in such a way that the movement cost is again equal to the hit cost. So pictorially, what this means is we choose a level set b of lambda t, and we will project xt minus 1 onto this xt. So I want to emphasize, once again, we choose the level set in such a way that the movement cost is equal to the hit cost. And what we show is that online balanced descent is actually a square root kappa competitive algorithm on kappa well-conditioned functions. What's more, this is actually tight in the sense that this analysis cannot be improved. We show an instance where it does actually achieve a square root kappa competitive ratio. So in the remaining few minutes, I'll give you a proof idea of how we prove this result. And the main idea is we use a potential function. In particular, the potential function is the distance to opt, where opt is the algorithm that knew all the functions beforehand and moved to minimize that. And what we'll show is that the cost of the algorithm at step t plus the change in potential is at most square root kappa times the cost of the optimal algorithm at step t. Summing this over t and observing that the potential is non-negative, this immediately implies that the algorithm's cost is at most square root kappa times the optimal cost. Okay. So let's go into the analysis. The analysis can be split into two parts. The first part is when opt is expensive. In particular, we say an opt is expensive if the hit cost of opt is at least half of the hit cost of the algorithm. And this case is in some sense very easy because we can just charge the cost of the whole algorithm to the cost of opt. So the most interesting case is when opt is cheap. In particular, the hit cost of opt is at most half of the hit cost of the algorithm. Let me draw a picture. In this case, opt has been projected to the level set lambda, which is the outer ellipse. Alg has been projected to the outer ellipse, whereas opt lies in a much smaller ellipse. So maybe it lies at yt, which is at the ellipse defined by the level set of lambda over 2. And one thing we can do is we can use the cosine law to relate all three sides of the triangle formed by xt, yt, and xt minus 1. If we do a little bit of algebra, we get a very interesting identity. In particular, the left side of the identity is exactly the movement cost of alg, and the right-hand side of the identity is proportional to the difference in potential. In particular, observe that the movement cost is half of the total cost of the algorithm, since the movement cost is equal to the hit cost. And the right-hand side is exactly the difference between xt and yt, which was the potential at times t, and xt minus 1 and yt, which was potential at t minus 1. So these two quantities are related by the secant of the angle theta. So if we can control this secant value, we will have a good understanding of how the cost of algorithm can be traded with the cost in the decrease in potential. And this is the key lemma that we prove in the paper. We show that this angle, in some sense, cannot be too small for well-conditioned functions. In particular, if your function is kappa well-conditioned, we can bound negative secant of theta to be at most 2 times square root of 2 kappa. If we choose alpha to be at least square root of 2 kappa, then what we show is that the cost of the algorithm is paid for by the decrease in potential. And this in turn implies that the algorithm is square root kappa competitive. Okay. So let me summarize in the last 30 seconds. For kappa well-conditioned functions, we give you an upper bound of square root kappa and a lower bound of kappa to the 1/3. And this is in the paper where we show for k-dimensional subspace chasing, we give an upper bound of roughly k and a lower bound of square root k. And the main open question is, can we close these gaps? Thank you.